Okay. It's a pleasure to introduce Claudius Zibrowius, and he's going to tell us about Rasmussen invariance of Whitehead doubles and other satellites. Thank you.
Okay, thank you very much for inviting me. It's a great pleasure to at least join you virtually. I'm going to talk about joint project with Lukas Lewark, which builds on an earlier collaboration together with Artem Kotelskiy and Liam Watson. I want to start this talk with a little construction. We start with some knot, okay, in this case, the trefoil knot. And the first thing that we do to our knot is we cut it open at some point, like so. Okay, and that gives us a 1-1 tangle, a tangle with one end at the top and one end at the bottom. And then we take a second strand, this yellow strand over here, and we tie it into this 1-1 tangle, like so, such that the two strands stay parallel throughout this tangle. Okay, from top to bottom, the blue and the yellow strands stay parallel. And this gives us a 2-2 tangle, a tangle with two ends at the top and two ends here at the bottom. And this is an interesting tangle with interesting properties. For example, if I take the top two tangle ends and glue those together like so, and I do the same on the other side, I get a knot. Which one is it? Would anyone like to guess?
The unknot.
The unknot. Okay, very good. Talking to audience of knot theorists. Okay, and I can prove this to you by simply unknotting these two strands. Okay, so that's one interesting property of this 2-2 tangle, or also known as Conway tangle, obtained by doubling a knot. Okay, are there any other properties? Well, for example, I could close this tangle in a different way. For instance, I could glue the two yellow strands together and then the two blue tangle ends. Okay, and this would give me a two-component link. Okay, but there is some ambiguity here. So, for example, I could also, before gluing yellow and blue together, I could also add maybe a full twist to these two strands and then then glue yellow to yellow and blue to blue. And this would give me a different two-component link. How could I distinguish those? Okay, adding a single twist, how can I distinguish these two links?
Linking number.
Linking number. Okay, very good. So the linking number changes by 1, and in particular, that tells us that that we can achieve, by adding a sufficient number of twists, we can achieve that this link, that this closure has linking number 0. And that's the kind of framing that I want to put on this Conway tangle. Let's write this down. So we started with our knot K. Then we cut it open, get a 1-1 tangle. Then we double it, and then we add a certain number of twists. And this number of twists is determined by two properties, namely that the second property here, that the 0 closure, i.e. when we glue yellow to yellow and blue to blue without adding any additional crossings, such that this link has linking number 0. Okay, and this, of course, does not change this first property, that if I take the infinity closure, i.e. the vertical closure, then I still have the unknot. Okay, and so this gives me, for every knot in the knot table, I get an interesting Conway tangle that I can study. So, well, when I have one Conway tangle, I can always take a second tangle. Here's a second Conway tangle. I hope you can see this. This is my favorite pretzel tangle, 2-3 pretzel tangle. And now if I have two Conway tangles, I can glue these two Conway tangles together. Okay, so like this and like this. Okay, I also have a picture on the slide, I guess, somewhere. There it is. Okay, maybe upside down. Okay, so well, that's an interesting knot, I guess. Yeah, it's a knot because it's only one component. Can anyone tell me something interesting about this particular knot? For example, is it hyperbolic? Would anyone like to have a guess? Yeah, so I take this.
Not a star. No, no, it's not. No, it's not central torus.
It's a torus. Yeah. So
It's not.
So it's not. Yeah. So this is not a hyperbolic knot because this is a satellite knot. And how do we see this satellite? Well, here's the torus. Okay, this torus swallows this Conway tangle, this orange and green Conway tangle, and then follows the blue and yellow strands around our companion knot. Okay, so we have the pattern of the satellite knot is entirely determined by what's inside this Conway sphere. And the companion is the knot that we started with, our trefoil knot. Okay, and well, this gives us, this is a satellite knot, okay, and conversely, whenever I have a satellite knot, PK, so with companion K and the pattern P, then I can always express this as a union of two Conway tangles, one for the pattern and one for the companion, well, as long as I have the correct wrapping number of the pattern. The wrapping number is defined as the minimal geometric intersection number between the two, between the pattern and this compressing disk of the torus. Okay, and I can generalize this construction a bit by, well, I get the twisted satellite knots by taking the original pattern knot and pattern tangle and companion tangle, and then adding some number of full twists before I glue them together. In this way, I define the T-twisted satellite knot P sub T of K. For instance, well, this would be, I guess, this diagram here would show the +3 twisted satellite knot with the same pattern as before and the same companion. And this number 3 tells us that we've undone those twists that we see up here in our companion tangle. Okay. The main theorem that I want to tell you about is originates from this very generic question that you can ask about any given knot invariant. You can ask, well, can I compute this knot invariant of on a satellite knot by doing two independent computations, by first doing a computation for the pattern, and then doing a computation for the companion, and then somehow putting these two pieces back together. An example of how this can work in practice is this well-known formula for the Alexander polynomial of a satellite knot. We can compute this, the Alexander polynomial of a satellite knot, as the product of the Alexander polynomial of the pattern evaluated at the unknot. Okay, so we just replace the companion by companion K by the unknot, and multiplied by the Alexander polynomial of the companion evaluated at, okay, there we have to change the argument to T to the N, where N is the winding number of the pattern. The winding number is almost the same as the wrapping number, except with signs. So we count the number of intersection points of the pattern with a compressing disk with signs. The question that our theorem sort of tries to answer, well, at least in a direction. I'm not going to answer this in general, but in the simplest non-trivial case is, well, what about the Rasmussen invariant? Can we somehow understand the Rasmussen invariant of a satellite knot, such as this satellite knot here? Can we understand that from the two pieces by one computation for the pattern and one computation for the companion? Now, some previous speakers have already introduced sort of Khovanov homology, and so I'm not sure how much I need to tell you about these Rasmussen invariants. So briefly, the Rasmussen invariant is an integer invariant that you can extract from an equivariant version of Khovanov homology. How this is done, I will explain later on towards the end of my talk. But for now, let's just take this as a black box invariant. It's some integer, actually an even integer, which you can extract from this Khovanov homology. In fact, it's not just a single integer invariant, but it's a whole family of invariants because there's a dependence on the field of coefficients that you compute Bar-Natan homology over. So originally, it was defined by Jacob Rasmussen over the field of characteristic 0. And then it was quickly extended to other characteristics, to general characteristics. So C will be some fixed characteristic, i.e. 0 or some prime integer. Okay, and this integer invariant has some interesting properties. As we already heard yesterday in Peter Feller's talk, it is a lower bound on the smooth slice genus. And moreover, it gives rise to a concordance homomorphism. Homomorphism from the smooth concordance group to the integers. Now, our main theorem is the following. For any knot k, we can define an integer that we call θ2 of k, such that with the following properties, namely that for all patterns with the correct winding and wrapping numbers, i.e. exactly the same winding and wrapping numbers as this satellite knot, okay, wrapping number 2, and winding number is 0 because, well, if we look at this picture here, then it goes in through the disk. Imagine disk sitting here at this point, and it goes in this way and then comes out from the other side. So this satellite knot has winding number 0. So for such patterns, we have the following formula for computing the Rasmussen invariant. The Rasmussen invariant of the satellite knot is equal to the Rasmussen invariant of another satellite knot, which is simpler than the first because we can replace the companion tangle simply by the unknot. So in a similar way as for the Alexander polynomial. And then there's only one dependence on the right hand side on the companion, namely in this twisting parameter, which is exactly determined by this integer invariant that we define for knots. Let's look at an example. First a corollary. Why is this interesting? Formal argument, which I'll explain later on, shows you that this integer invariant θ2 of k is interesting. It defines a concordance homomorphism, and as we will also see, this concordance homomorphism is different from the Rasmussen invariant. Okay, but now some examples. These theta invariants can be computed, for instance, the trefoil knot, the positive 2-3 torus knot, has theta invariant equal to 4. Okay, which means, okay, let's plug this into our theorem, which means that the S invariant of any satellite knot with companion equal to the trefoil knot is equal to the Rasmussen invariant of, well, the pattern that we have here, but with 4 twists evaluated at the unknot. Okay, so in pictures, well, here we have, here on the left, we have our original satellite knot whose Rasmussen invariant we want to compute. And on the right-hand side, we have replaced this companion tangle by the trivial tangle. And the only thing that we've changed otherwise is we've added a number of twists in the pattern. Okay, and this holds for any pattern. Okay, so we've really split the computation into 2 parts. One for the companion, that's the information in theta, and then the other information is the pattern itself. And yeah, this holds for any of these patterns, all of which have winding number 0 and wrapping number equal to 2. Any questions up to this point? Okay, so the plan for the rest of my talk is now the following. First, I want to explain to you what the effect of this, what the effect of twisting is on the Rasmussen invariant. So how much does this theta invariant actually what effect does this theta have on the Rasmussen invariant? Then I want to prove this corollary, how just knowing this equality for all patterns, how this implies that the theta invariant is concordance homomorphism. And then finally, I want to explain to you sort of the key ideas that go into proving the main theorem. They rely on these multicurve invariants that I've developed together with Artem Kotelskiy and Liam Watson for conway tangles. And then, time permitting, if there's I will tell you a bit about the winding number 2 case. Okay, any questions up to this point? Maybe just as a teaser, sort of where does this theorem come from? Well, it comes from these multicurve invariants, and this mysterious integer invariant theta 2 of k has a geometric, very concrete, explicit geometric interpretation in terms of these multicurve invariants. Any questions? Statement clear?
A question. In terms of generalizing these results, do you expect that you will get something similar to your number theta for winding numbers bigger than 0, specifically on number 1? Or do you expect to see more dependence on your opinion?
I would expect not to see just a single integer, but maybe a sequence of integers. Sort of for each, when you increase the winding number, I would assume that you would see a sort of for winding number n, you would see n minus 1 integers, but that's just a guess, I think. I don't know how to generalize these two arbitrary windings. It is very specific. So methods that go into the proof of this theorem are very specific to both Khovanov homology and also to the winding number, to the wrapping number 2 case. Okay, let's proceed. Before I proceed, from now on, all patterns will have these winding and wrapping numbers, winding number 0 and wrapping number 2, so that we can, precisely in the case of this example here. The effect of twisting on the Rasmussen invariant is actually a general phenomenon that can be understood more generally for any sliced torus invariant. We already heard yesterday about sliced torus invariant, so just a brief reminder: a not invariant, an integer invariant is called a sliced torus invariant if, first of all, it induces a concordance homomorphism, and secondly, if it gives a low bound on the smooth 4 genus with equality exactly for the positive torus knots. And examples are, well, for instance, these Rasmussen invariants, and then on the other side also this Szabo tau invariant from knot-flow homology. To understand twisting, well, let's look at a triple, at a fixed triple. We have a fixed sliced torus invariant mu. Think of Rasmussen invariant or half the Rasmussen invariant. Then fix a pattern and some knot k. And then we consider this function. So we consider the sliced torus invariant of these twisted satellite knots as a function in t, in the twisting parameter. And the following proposition, which is not hard to prove, says that this function is either a constant, it's very boring, or it is, well, almost boring. It's just one interesting piece of information in there, namely it has a single jump by -1. So it stays constant for a while, then it jumps down by 1, and then it is constant again. And we call this jump point, okay, so the point on the right-hand side of this jump, we call this the jump point, and we denote this by theta nu of p of k, if it exists, and if this function is constant, then we just set this number equal to infinity. Furthermore, we define two other theta invariants, one for patterns and one for knots, by specializing the other component respectively. So we define the theta invariant for a pattern by fixing the companion to be the unknot, And similarly, we define the theta invariant of a knot by fixing the pattern to be the positive Whitehead pattern. So here's a picture of a positive Whitehead pattern. It's this clasp, and then here in this instance for the trefoil knot. This proposition is not hard to show. Let's do this we do this in two steps. First of all, we want to show that this function assumes only two values, two consecutive values. So it suffices to see that, well, the absolute value of the difference between any two of these any two values of this function is at most 1. Okay, so let's look at this example here. So let this be, say, maybe p sub t, p sub t of k. And now we want to get to the other the other satellite knot with a different twisting parameter. Okay, and that's not too hard. Okay, we want to construct a concordism from one to the other, and we do this by first attaching a band along this path here. Okay, that gives us this picture. Okay, and now we can, well, add as many twists as we like here on the right-hand side. For example, here 2 twists, and then we can again add another band like so. Okay. And that way we can get to any other twisting parameter in this family. Okay, and we've only used 2 bands, there's now a concordism of genus 1. So yeah, formal properties of slice-Torus invariance then tell you yes, this inequality really holds. The second step is a very similar argument. I mean, this first argument also, I guess, goes back to a paper of Livingston, where you just look at, construct explicit concordisms between certain knots. And so what this second piece tells you is that, well, there's if you look at the difference between two consecutive twisting parameters, then you can only go down. Either you stay constant or you can go down. Okay, and these two properties combined will tell you that you can only see at most 1 jump, and it goes down. Any questions about this proof? If not, then let's move on and look at some examples for how you can use this proposition in practice. Well, for example, let's look at this very simple example where we have the pattern equal to the positive Whitehead double, so the positive Whitehead pattern, just this clasp. And let's evaluate this on the unknot. That's this picture here. So up here, there's the trivial tangle. There's the companion tangle corresponding to the unknot. And this is indeed, this diagram on the left is the diagram of the unknot. So any slice-Torus invariant takes the value 0 on this knot. On the right-hand side, we take the twisting parameter to be equal to -1. And one can see that this is equal to the positive 2-3 torus knot. And so there, the value of any slice-Torus invariant is equal to 1. Okay, and well, this means that we've exactly found the jump point in our function. Okay, this tells us, well, it tells us the value at -1, there it is 1, and at 0 it is 0. So there's the jump. We have a jump at 0. So using this proposition, we now know, okay, this slice-Torus invariant of this family of twisted positive Whitehead patterns evaluated at the unknot is looks like this. Said in another way, this means that this theta invariant of evaluated at the unknot is always 0. Okay, for any slice-Torus invariant. Now let's come back to our main theorem. This said that we can compute the Rasmussen invariant of any satellite knot by replacing the companion tangle, replacing the companion by the unknot, and then simply adding a certain number of twists, which is determined by this theta2 of k. And as the notation already suggests, is that, well, that this theta2 is precisely the theta invariant, the theta nu, for nu equal to half the Rasmussen invariant. And it is, again, also not hard to show now that we have, now that we know that theta nu of the unknot is 0. Namely, well, we simply apply this identity here to the this family for which we understand the theta invariant and the slice torus invariance. What does this give us? Well, this gives us on the left-hand side, there we have our satellite knot, okay, our Whitehead, twisted Whitehead doubles of the knot K. And on the right-hand side, well, we've removed the dependence on K altogether, except for this twisting parameter. And this holds for all T. Yeah? I mean, the theorem holds for all patterns. And now we can look at the jump points, sort of at the theta nus of both sides. On the right-hand side, well, there we have, well, some twisted Whitehead double of the unknot. That's exactly the computation that we've done up here. And this computation tells us, well, this function here on the right-hand side has a jump point when this value here is 0, i.e. when t is equal to theta2 of k. So this the right-hand side has a jump point precisely when these two values are equal. And, well, the left-hand side, well, it's either constant or has a jump point, but we already know that the right-hand side has a jump, so the left-hand side also has to have a jump because they're equal. So we know that the left-hand side has a jump point precisely when t is equal to theta sub nu of k. Okay, so in summary, yeah, the left-hand side jumps at theta nu by definition, and the right-hand side jumps precisely at 0 because of our computation. Okay, and that proves that these two invariants have to be the same. Our methods for proving the main theorem are very particular, as I said, very particular to Khovanov homology. And so, but still, we might ask, okay, these slice torus invariants, they all have this nice property. You can define these integers for all slice torus invariants. So does this main theorem also hold for other slice torus invariants? Before I go into that question, let me say that these theta nus of case, these theta invariants, they're not entirely new. So they have been studied before by Livingston and Naik under different name T sub nu, and the only difference is a single shift. And the reason why we make this shift is because, well, at least for the Rasmussen invariant, the theta invariant is a concordance homomorphism. Okay, so if you don't do that shift, this T sub nu of k, that's not a concordance homomorphism. At least for the Rasmussen invariant. And also this theta invariant, as I said earlier, this has a very explicit geometric interpretation. So this invariant here is a bit more natural than the T sub nu. They showed in general that these theta invariants are finite. Which follows for the S invariant from our theorem, but one can actually show this in general. So this question really does make sense. So we know that these thetas are really finite; they're integers. Okay, so we can ask, well, is there a corresponding theorem for other slice torus invariants? For the tau invariant, we can say the following. This goes back to a theorem of Matt Hedden. He computed the knot-flow homologies of general Whitehead doubles and twisted Whitehead doubles. And from this, as a corollary, he got computations of the tau invariants of these twisted Whitehead doubles, and repackaged now in the language of these theta invariants, his theorem boils down to this computation of theta, the sort of jump point invariant associated with theta. And his theorem says, well, it is a very simple invariant. You just recover twice the tau invariant. Okay. So he computed this for twisted Whitehead doubles, but of course now you can ask, well, what about other patterns of this of the correct winding and wrapping numbers? And this is an open question that I'd like to invite people who know more, sort of, who have, yeah. I invite people to think about this question. Is does this identity, it holds for the positive twisted positive Whitehead doubles, but does it hold for arbitrary patterns of the correct wrapping and winding numbers? Another perspective, before I continue, another perspective on Mathedon's theorem is that, well, if this were true, okay, if this identity was true, then this tells you that, well, as I will tell you in a moment, the main theorem implies that whatever this invariant is, this theta invariant, that it is a concordance homomorphism. And what Mathedon's theorem tells you is that, well, in the case of the tau invariant, you don't get anything interesting from it. Okay, you just recover twice the tau invariant. And interestingly, that's different on the Khovanov side. So that's another point where the two theories diverge. You can also ask this question about Rasmussen invariants for other coefficients, and this is something that we really expect to be true. So the methods that we apply to prove our main theorem, they should generalize immediately. It's just that the methods are currently furthest developed over characteristic 2. Historically, these twisted Whitehead doubles have played an sort of important role in sort of trying to understand slice torus invariants. For example, they were the first sort of twisted Whitehead patterns of the trefoil knot. They were the first examples where tau was different from the S invariant. And we can now reinterpret this result, these examples, as saying the following: well, that the theta invariant associated with tau, which is according to Mathedon just twice tau, is 2, but the theta invariant for the trefoil knot for the Rasmussen invariant, when you compute with in characteristic 0, is 3. Okay, so on the right hand side, we have not jumped yet. Okay, there's still 1 because the twisting parameter is 2. On the left hand side, we've already done the jump. So the jump points are exactly one apart, and that explains why these two invariants are different. I promised earlier that well, in the Khovanov side, on the Khovanov side, things are really more interesting than in the Hegar-Fleur side. And this is the following fact. It's just a computation of some examples that show that the theta invariant and the S invariant, they don't, there's no direct correspondence. The S invariant does not determine theta, unlike in Hegar-Fleur homology. Okay. Let me also say briefly a few words about coefficients. So the first examples where the S invariants are shown interesting behavior when you change the characteristic. First examples of this kind were found by Kotelskiy about 10 years ago. He found examples where the S invariant over characteristic 2 is different from other characteristics. And only last year, Lukas and we found first examples where we also see an interesting behavior in characteristic 3. And we wrote this little postcard that some of you may have received to celebrate this discovery of this example. And we actually, we now, I guess we expect that all these Rasmussen invariants are different Dixit has some conjectures about how you might find them, but at the moment the computational techniques are not optimized to get there with current computer technology. Okay, I think there's a good place to stop and ask for questions before continuing. Okay, there don't seem to be any questions. Okay, if there are questions, please interrupt. I guess in the interest of time, I will skip the proof of this corollary, but let me just say this is really a very simple exercise. Maybe I should leave this as an exercise. Okay, so let me quickly skip through these slides and go straight to the proof of the main theorem. Well, the main theorem tells us something about how the Rasmussen invariant changes or does not change under a certain tangle replacement. Before I describe sort of what goes into the proof of this, I first need to tell you about, well, what the Rasmussen invariant is and where it comes from. Okay, as I said earlier, the Rasmussen invariant is an integer that you extract from an equivariant version of Khovanov homology, which is known as Bar-Natan homology and takes the form of a bigraded F-adjoint U module, where F is some field of some fixed characteristic C. For example, for the trefoil knot, the Bar-Natan homology looks very simple. It consists of a free part, so just a copy of F-adjoint U shifted in a certain bigrading, homological grading, and then this additional integer grading, the quantum grading. And then there's the second part, which is U torsion. In fact, in this case, just a single copy of the ground field, again shifted in homological and quantum grading. And this is the general sort of the structure of Bar-Natan homology, which one can prove. We have the following structure theorem, which says we always have one free summand. Okay, maybe not canonical, but yeah, we have one free summand, and then the rest is torsion. The free summand always lives in homological grading as 0 for knots. And then there's one interesting piece of information in this free summand, namely the quantum grading. And this quantum grading is precisely the definition of, that's precisely the Rasmussen invariant, the quantum grading of this tower, of this single copy of F-adjoint U. For instance, here for the trefoil knot, the S invariant is equal to 2 because the quantum grading is 2. Okay, so now we go back to our main our satellites. Okay, and well, we wanted to study how, well, we want to study the Rasmussen invariant of these satellites by decomposing, well, by doing two separate computations. One computation for the pattern, i.e. for the pattern tangle, and one computation for the companion tangle here. And so, yeah, we already have kind of the decomposition on the level of our geometric object into two tangles, pattern tangle and a companion tangle. Okay, so what is needed is some kind of relative version for this Bar-Natan homology. And the well, we've already seen in what was mentioned in the previous talk, this Bar-Natan sort of Bar-Natan's concordance category. So there are algebraic constructions, algebraic invariants for that generalize Khovanov and Bar-Natan homology to tangles. Okay, they're due to various different authors. Bar-Natan is, I guess, the most popular one. And but all these invariants, well, they're algebraic invariants. They're usually objects in some derived category of some algebra, i.e. some chain complexes over algebras, which in general arbitrary tangles can be quite complicated. But it turns out that in this case here that we're interested in, namely, well, where we have the wrapping number 2, where we have this decomposition into 2 Conway tangles, then in this case, we have a nice reformulation, topological reformulation of Bar-Natan homology. And this looks as follows. This is the main sort of the central part of this this machinery that Artem, Kotelskiy, Liam Watson, and I developed, which says that, well, given any decomposition of a knot into 2 Conway tangles, we can compute the Bar-Natan homology of our knot by first doing 2 separate computations, namely for the 2 tangles T1 and T2. These are these multicurve invariants associated with T1 and T2. Okay, so some gadgets. Okay, let's take these as black boxes for the moment. And then there's some machine that takes these 2 pieces and churns out the Bar-Natan homology. Okay, before I tell you more about these multicurves and this wrapped Lagrangian flow homology, whatever that is, let me briefly sketch the proof of the main theorem, because now it's so formally it's very straightforward. We want to compute the S invariant of a satellite knot P of K. Well, we take our decomposition into companion and pattern tangles, and we apply our gluing theorem. Okay, says, well, okay, if we want to compute the S invariant of this knot, it suffices to extract the S invariant from, well, from the Bar-Natan homology, from this wrapped Lagrangian flow homology of the 2 pieces of the multicurve associated with the pattern and the multicurve associated with the companion. And now the key step is that we can now replace this this multicurve for the companion by a certain curve, namely the multicurve that we associate with this very simple looking tangle, namely the rational tangle with just a number of twists, and the number of twists is precisely determined by this theta invariant of K. This is the main step, and once we've done this, then it's again an application of the gluing theorem, but just backwards. So yeah, and we get this tangle decomposition. So this was starting satellite knot, okay, and now we take out this companion tangle, and we replace it by this tangle R, which is just this this tangle here, okay, just number of twists, and we glue it back in. Okay, and we have got this simpler satellite knot. Okay, so that's the strategy. So from a bird's eye, yeah, sort of, yeah, zoomed out version. So now, maybe before I move on, are there other questions?
Yeah, I have a question. And
yeah,
feel free to postpone this until like after the talk. But did you sketch, like, I guess I've never seen Bar-Natan one before. Do you sketch like how it's constructed or what it is?
How it is constructed? Yeah, it's exactly constructed in exactly the way that you define it in your talk, right? It's Matt. No.
Yeah. I mean, why? What is you like?
Okay, so it's you take the construction from the previous talk, and the only thing that you change is you remove dots. There are no dots, and you you just work with the honest concordism category with just 2 relations, namely the sphere relation and with the 4 tubes relation.
Right, but is this?
And then this, and then you do the following. So Khovanov homology, from my perspective, is most natural when you have a base point in your knot. Okay, so you actually regard things as 1-1 tangles maybe. And so there's always one distinguished component when you compute your Khovanov homology, Bar-Natan chain complex for a knot. There's always one distinguished component, and this action, this variable u, corresponds to adding genus to that distinguished component. Okay, so if you just compute the endomorphism ring of the simple of the 1-1 tangle of the trivial tangle in Bar-Natan's concordance category,
Okay.
then this endomorphism ring is isomorphic to F adjoint U.
Okay, sorry, I understand. So you don't kill genus 3 4. I'm sorry.
No,
Okay.
yeah.
I'm good.
Yeah, keep them alive. Okay, other questions? Oh, sorry. What am I doing? What am I doing? Okay. Okay, sorry. Okay, I'm back on track. Were there other questions?
Can you talk a little bit where that step starts?
Yes, that's what I'm going to talk about. Okay, very good. Okay, so I should move on. So what about this step star? Well, in order to tell you more about this step, I first need to tell you a bit about these multicurves and how this pairing theorem works in practice. So let's do this in sort of definition by examples. So here we have a decomposition of a trefoil knot into 2 Conway tangles. And well, as I mentioned just a few moments ago, I always want to keep sort of add a base point to my picture, to my knots. Okay, so I place this on this Conway sphere that decomposes this trefoil knot into 2 Conway tangles, namely these 2 Conway tangles, the trivial tangle, 2 horizontal strands, and then this other Conway tangle, these 2 strands with 3 twists, the inside of this picture. And now the multicurve invariant that we associate with these 2 very simple tangles, it takes the form, or generally these multicurve invariants are collections of curves on a 4-punctured sphere. Not just any 4-punctured sphere, namely the 4-punctured sphere, which is the boundary of the 3-ball containing the tangle. So it's exactly as I've drawn them here. So this red curve here, this interval, is precisely the invariant of this trivial tangle. Okay, it looks very simple. And similarly, this blue curve, gamma 2, that is the invariant that we associate with this 3-twist tangle. Okay, and we consider these curves up to homotopy. There are 2 types of curves. There are embeddings there are maps from intervals, paths on the 4-punctured sphere. They're supposed to always end on the non-special tangle ends, one of these 3 tangle ends. And in fact, they end always on, so not just in these examples, but in general, they always end on the 2 tangle ends that are connected by a strand. Okay, so for instance, this tangle strand down here, if the other end of the curve, gamma 2, is up here, and if I go through the tangle, I end up at the same place. Okay, and that's true not just in these examples, but that's a common sort of a general property of these multicurve invariants. Okay, so there's this type of curve, these non-compact components, maps from intervals to the 4-punctured sphere, considered up to homotopy. And then there are also compact curves, so maps from circles into the 4-punctured sphere. But for the purpose of this talk, we can completely ignore those. Okay, so these are these multicurve invariants. Now, what about this gluing theorem? Well, this gluing theorem tells us that we can compute the Bar-Natan homology of this knot K, of this trefoil knot, by taking the wrapped Lagrangian Floer homology of the 2 multicurves, i.e. gamma 1 and gamma 2. And this is illustrated here in this picture. The gamma 2 curve looks as before, here on the right-hand side. The red curve is, well, almost the same as this red curve, except that we add these little wrappings around the tangle ends. And this gives us some intersection points of the red curve with the blue curve, namely this single intersection point down here, and then, well, infinitely many intersection points around this tangle end. So in the picture, well, okay, so these infinitely many intersection points, they correspond exactly to this free part to this tower, to the copy of F adjoint U. Oh, sorry, these should be U's. Yeah, H is equal to U. Apologize. So they correspond to to this free summand, to this tower, and then this single intersection point that corresponds to this intersection point here, to the generator in Bar-Natan homology here. Let's look at a second example, which is almost the same as before, except that I've now taken the blue tangle hasn't changed. We've now taken the infinity closure of this 3-twist tangle. And well, now the red curve has changed. It's now this this trivially embedded interval. And now I can also again look at this intersection picture, and I see now, well, now I see only this tower up here in this corner. Again, this should be U, and again I see only one tower. Let's look at a third example. So there's this companion tangle from earlier, where you have it. Is this companion tangle here, double trefoil knot. And again, and now I can ask myself, okay, what are the restrictions? What does this invariant look like? And there are some general things that we can sort of in general for arbitrary tangles. These Bar-Natan invariants, multicurves, they can look really complicated. But in the case of these companion tangles, there's a certain structure to them. And this structure comes from the fact that, well, we know that they're cap trivial. They have this unknot closure. And this means that they intersect with this arc here, with the tangle on the invariant of the tangle on the outside. They intersect trivially with this arc here on the outside, just as in the previous case. We just see, we know that, well, blue curve could do anything, okay, in this 4-punctured sphere, but we know that, well, there are two things what we know. We know it starts at this tangle end down here, and we know it ends on this tangle end down here. That's because of the connectivity detection result. And secondly, we know that there's only this single tower, okay, because we're computing the Bar-Natan homology of the unknot. So we know that this blue curve, whatever it does, it always has to avoid this red arc here on the right-hand side. Okay. And this puts very strong restrictions on what the multicurve invariants can look like in general. And to see this, it's best to look at a certain covering space of the 4-punctured sphere. So this covering space is just the plane minus the integer lattice points, which you can think of as the, well, you take the 4-punctured sphere, now you take the 2-fold branch at the 4 tangle ends, at the 4 punctures. That's the torus. And now you take the universal cover of the torus and then cut out the integer lattice points. Okay, so the preimage of this gray circle here are the gray squares in this picture down here. Now I said the blue curve, whatever it is for this tangle, it has to avoid this red curve. So in this covering space picture, well, it also has the preimage of that, well, any lift also has to avoid these two red lines, the lift of this red interval. So, well, okay, what could it look like? We know, okay, we know it ends at this point. It starts down here, ends down there. Okay, so maybe, well, okay, looks something like this. Okay, it starts at this puncture, which corresponds to this puncture over here. Okay, it goes in some direction, and then, well, it does something in between, and then ends at this other tangle end, which corresponds to this puncture. Okay. Now, if you think of so people who are familiar with these multicurve invariants for 3 manifolds with torus boundary will already be familiar with this kind of game. If you now imagine this picture as, well, sitting in the plane, and the integer lattice points are wooden pegs, and this curve is made out of rubber, I could now pull this curve tight. Okay, and what I would see is that a picture like this. So this becomes just a straight line. And then I would go up there and then back again. So it's really, maybe I can highlight this. We'd see some piecewise linear function, namely this function here and this function here, or curve rather. So we see a curve segment that's staying close to this vertical line, okay, slope infinity, and then we see one finite slope part, okay, and it's this finite slope part that's exactly theta, because now what we can do, well, we now want to replace this companion tangle by a simpler tangle, by this end twist, by this twist tangle, and these twist tangles, okay, here it is. These twist tangles, these twist tangles, they have a very simple looking multicurve invariant, right? They're just these embedded arcs on the four punctured sphere, okay. And in this case, for I guess the four twist tangle, we have this arc which in the covering space has slope 4, which is near this, or sort of at the beginning of this blue curve, stays very close to this blue curve. So this green curve, this green dashed line, approximates this blue curve. And so this is the reason why we can then, well, hope it's not too hard to believe then that if you replace the blue curve by the green curve, right, then the Bar-Natan homology, or the part of the Bar-Natan homology that corresponds to, sort of, that happens around this tangle end here, does not change. Okay, so very briefly, let's sketch this. Maybe that's the last thing that I do. Let's sketch this, the proof of this identity, that we can really replace this blue curve by the green curve, by the simpler curve. This follows from the fact that that we have this restriction on this, that we know that the companion tangle has this very nice property that is cap trivial, which in consequence means that this curve has exactly one finite slope. Okay, it might have these infinity slopes, might do something complicated here on this vertical line. Okay, but we know it has exactly this one segment that has finite slope, and this theta invariant is precisely half that slope. Right? It's equal to the number of full twists corresponding to in this rational tangle. Here are a couple of examples for the trefoil. Not the companion tangle has this multicurve invariant, and there the slope is 8, and so, well, the theta invariant is equal to 4. For the figure 8 knot, the multicurve invariant looks very simple, and it's just this simple interval, looks like the invariant for this trivial tangle, and for the this 3-4 torus knot, the theta invariant is 8, and there the curve looks like this. It's almost, yeah, it's a bit small, but yeah, there's slope is 16, and then the curve does something complicated in between. Okay, maybe there's a good point to stop. Thank you.
Hi, Claudius. So I think, please remind me if I just have this memory wrong. I remember Matt Hedden's paper, but is there another paper about highly twisted Whitehead doubles and S invariant? Do you recall this as well? Like not the zero frame Whitehead, but when you have like sufficiently number of twists, there's like some formula.
Yes, so there are various papers. So I think that there's a paper by Kot and I think Robert Lawrence. But I might be wrong. Okay, so there are several papers that have sort of that tell you the sort of versions of this proposition that I proved earlier, that there are only there's only one jump in the case of wrapping number 2. But if you have a higher wrapping number, then there can be more jumps in between, but it always goes in one direction. I'm not sure whether you're referring to that paper.
Not wrapping number, like just twist. We don't have to talk about it now. I was just wondering.
Yeah, and please let me know if you, yeah, I mean, yeah.
I was supposed to do this, I think, and I forgot.
Sorry, can you repeat the question?
It wasn't a question. She was just changing the view.
Sorry. Okay.
All the speakers,
Okay.
all the participants.
Can I ask a question? Yeah. Sure.
You have a question?
Yes. So you said if winding number is 1, then you expect to get more than one integer slope.
When winding number is
More than 0. It's not.
so if winding number is not equal to 0, if it's plus minus 2,
Mhm.
then yeah, then things get more interesting. So that was the sort of the last slide that I was had prepared. So yeah, what can we say about this case where winding number is equal to 2? Was that really the question?
Yes, yes.
I'm just using the okay. Okay. So in this case, the winding number 2 case, there, well, things get a bit more complicated, and the reason for this, from the multicurve perspective, is that the S invariant for the unknot closures, or the winding number 0 closures, they are contained in this tangle end down here. So on the bottom right. Okay, and there we know, okay, there's this curve has some finite slope. Okay, and it's this by definition it's this theta invariant, and yeah, there's nothing really interesting going on there apart from that. But on the other side, okay, so here in the winding number 2 case, we need to look at the other tangle end, and there we have more interesting phenomena. So it can look like this. So it may just be that the multicurve invariant for this companion tangle looks like the invariant of a rational tangle. It's just this embedded interval. Okay, and in this case we call this invariant the theta rational. So if there exists some rational tangle, this n-twist rational tangle, such that these two multicurve invariants are identical. Okay, and in this case, we get a theorem that is almost the same as before. In the other case, well, if it doesn't look like this, not finite slope at this tangle end, well, then we're in one of these cases here in the trefoil, or okay, it's hardly visible. Okay, it's really small down here. So then we're at the other tangle end, and there we have slope infinity. Okay, so there's at least this dichotomy between finite slope and slope infinity. And in the slope infinity case, there are also 2 more separate cases, sort of positive infinity and negative infinity. And what this is really, so the way that I currently think about this is in terms of an analogy to Jen Hom's epsilon invariant. Okay, so how do I explain this? Well, this is the theorem that we prove in winding number 2 case when the companion knot is θ2 rational. Okay, then we have, so this piece here is precisely the thing that we had before. And then we just have this additional summand. Okay. And in comparison to sort of, yeah, this to Jen Hom's result is kind of the, if you look at, I would think of this theta rational, of not being theta rational, as corresponding to the epsilon invariant being equal to 0. And the reason why I say this is because, well, in the winding number 2 case, we're exactly in the case where we look at cables of knots. And there we, so the epsilon invariant, sort of the tau invariant, has a very interesting property again, which can be proved for arbitrary sliced torus invariants, namely that either it is a linear function, or it is linear except for a single jump. Okay, and in the case that it's that epsilon 0, this case corresponds precisely to the case where the function is linear, and the case where it's a jump is the case where epsilon is plus minus 1. Okay, and yeah. Right, and we see the same pattern also for the S invariant. So there's precisely a jump when there's precisely a jump when the companion knot is not theta2 rational. Yeah. So there are some interesting questions that you could ask here. For example, we don't know any example so far where the epsilon invariant is different. So where the epsilon invariant is 0, but the knot is not theta2 rational, or the other way around, where sort of at the moment it looks like the knot is theta2 rational exactly when epsilon is 0. But yeah, I probably wouldn't make a conjecture like this on maybe 50 examples that we've computed.
Thank you. Other questions? Okay. Great, let's thank Claudius again, and we'll get back at 2 p.m.
Okay, thanks.
Can you do iterated Whitehead doubling?
Say again?
Can you do iterated Whitehead doubling?
Iterated, I would love to. So we don't know how to do iterate. So at the moment, the computations are done just using computer programs, just brute force calculations, and we don't know how to. So we see certain patterns. So, not patterns in terms of satellites, but patterns in the. But we don't know how to do, for example, iterations. Yeah, that's an interesting question, whether somehow maybe the theta invariant of the Whitehead double is determined by S and theta. But yeah.
Does theta give a 4 genus bound?
That's another interesting question. So yeah, we don't know. I mean, we've looked into this, but we don't know how to prove something like this.
This is great.
Yeah, so it would be sort of there would be 1/4 of theta is genus bound, but also, I mean, the theta invariants, they also, I mean, as I said, you can define them over arbitrary characteristic, and they really are different. So in the example, already they're different for the trefoil knot.
But is it a genus bound for the examples that you have computed, or?
No, I don't think so. I mean, I don't know whether that's true or not. But it's somehow, I mean, yeah, the S invariant is a lower bound, but somehow this theta invariant is somehow sort of measures when there's a jump point when you twist, and yeah, I don't know how to relate that to any genus bounds.
Yeah, can I ask? So can you calculate the theta invariant from, like, okay, so do I understand correctly? So you take your knot, you represent it as a one angle, and you take the 2 cable of this. Can you calculate the theta invariant from the Khovanov complex of this tangle, or maybe a family of related tangles, like by taking this guy and twisting?
Well, okay, I mean, there are 2 ways how we currently calculate these theta invariants. One is by computing the tangle invariants, by computing these multicurve invariants. So I've written a computer program that can do this. Another way of computing this is just by this definition of where is the jump point. So you just look at certain closures of the companion tangle. Just compute this for a family of knots and vary the twisting pattern, and then you also know that yeah, at some point it has to terminate. When it terminates, you have found theta.
Is there, if you write down the multicurve invariant, is there a straightforward process that will recover the Khovanov complex of the symbol?
Yes.
Okay, so this.
I mean, this multicurve is a geometric interpretation of the Khovanov or of the Bar-Natan chain complex. So there's a dictionary how you can go for how any complex over the Bar-Natan category associated with a four-punctured disk, how you can go from any complex over that concordism category to a multicurve and back again.
Where should I read about that, or can you tell us?
Well, I mean, we wrote this paper 3 years ago. So we've written a series of papers, and this first paper, that's where we first. Actually, I mean, the starting point was actually a paper of yours and Matt Hedden and covered, yeah, where you did this constructed this functor from this dotted concordism category, I guess, to the Fukaya category. And that was the whole starting point of our construction. And so we extended this to the Bar-Natan world, and then proved the Fluing theorem and so on. But that was really the starting point of this whole thing.
Cool. Thanks.